So what we're going to do here is, as Lori said, the one-dimensional heat equation. We're basically going to do the hello world of numerical packages. Now, for a lot of people in here, you could probably do this in your sleep. But for a few people in here, this might be somewhat of an interesting exercise. And beyond that, it does allow us to kick the tires to make sure that we all have access to the machine. We're able to compile and run things there. And we'll find out sooner in the day rather than later as you get to the more important hands-on exercises later, whether or not there are any technical challenges. So the science problem we're confronted with is this very simple one. We live in a house made of solid wood walls with water pipes running into them. Running through them. I won't get into the details of how you engineer a house that way, but you have water pipes and solid wood walls. You keep the inside temperature constantly at 70 degrees, and a storm is coming. And you're going to have an overnight storm. It's going to get really cold, and it's going to drop down to 40 below zero. And the question is the water in your pipes going to freeze? So in order to solve this problem, this introduces, as Lori's mentioned, the heat equation. We're going to deal with the one-dimensional heat equation. This is a partial differential equation here. U is temperature, T is time, X is spatial distance, and alpha is a property of the material, in this case wood. It sort of says how quickly heat can move through that material. And our problem is to seek a numerical solution to this based on left and right endpoint boundary conditions and an initial condition. So what do we start with a PDE up at the top, and the first problem is we have to discretize this. And in this case, we'll do the left-hand side and right-hand side independently. We need to approximate the partial of U with respect to time. That's a very simple slope formula. So on the left-hand side, we take two temperatures spaced in time by delta T, take the ratio of that, and we can estimate the derivative of U in time. And likewise, for the second partial of U spatially, we do something similar, except we use a center difference formula there, and end up with a right-hand side discretized approximation of the second derivative. And when we do this, of course, we're breaking up space by delta X and time by delta T. And when we set the left-hand side and the right-hand side equal to each other, we get an equation with temperatures at times K and K plus 1. Now, the first question is, do you see anything here that kind of sort of looks like a mesh? And for sure you do. It's the simplest of all possible meshes, basically a structured mesh in this case. Uniform spacing, a fixed space in space, and a fixed spacing in time. You'll be hearing a lot about discretizations today, but we won't be dealing with structured meshes today. We'll be dealing with unstructured. Okay, so given this equation now for the temperatures at times K and K plus 1 in spatial positions I minus 1, I plus 1, let's see if we can rearrange terms and come up with an update equation. That's this equation here. This is known as the FTCS algorithm, forward in time centered space algorithm for this particular PDE. R is this particular ratio, and it's known to be unstable if R is greater than 1/2. So we're going to do our first hands-on exercise real quickly here. All right, and the first problem we want to do is basically implement that equation. Our exercise is basically to implement the body of this function, and my apologies, I'm not going to be able to actually show this equation on the screen while I write the code, but it should go relatively quickly here. So we'll just really quickly write this code. And now we have to write the update equation. So the array that comes in here is UK1. That's the array that we need to return from this method, and UK0 are the temperatures at the previous time. Okay, so just briefly looking at that, UK0, I plus 1, I minus 1. Okay, that looks correct to me.
Should be 1 minus 2R.
1 minus 2R. Thank you. That's the value of pair programming, right? Somebody's looking over your shoulder and can point out your own mistakes. Thank you very much. So once you implement that, you make it. Hopefully that works for everybody. I'll pause for just a minute to allow people to work through that. We do have time to pause for just a minute. Okay, so I'm going to jump back into the view graphs while you're still typing. The next question is, we've written some software here. How do we know that what we've written is sane at all? I mean, we could talk about testing in great detail. I won't do that, but the question is, can we think of anything simple we can do to ask ourselves if the code we just wrote is actually makes sense? And the answer is, we know sort of intuitively if you let the heat equation run for a really long time, it reaches a steady state. So the idea is let's do that with this software. Let's run it for a long time, see if the steady state it reaches is what we expect it to. And the simple answer is we can do that very quickly. So we just made it. By the way, if you do heat minus help, it gives a bunch of information on the arguments and what they mean. And in particular, you can see here that it has boundary conditions for the left and right ends, a temperature of 0 at one end and 1 at the other end. So we already have a boundary condition that would represent a line if we just let it run for a long time. So let's just let it run for a long time and see what happens. Using max t equals, 100 seconds. All right. And what did it just do? When it runs, it writes data to a particular directory. That directory is determined by this argument up here, our uname argument. So it stored those to a heat result. All right, stored various files there. Let's just output the final results. Anybody look at that and think that that's the right steady state for this one? Does anybody not think that's the right steady state? In other words, it's a line from 0 to 1, right? And so it did reach the correct steady state. So at least we have some confirmation that the software we just wrote is working correctly. I wouldn't say this was a rigorous test, but okay.
The two columns.
I'm sorry. The column on this column is the x's and this column is the y's. I'm sorry. So basically space and temperature. So back to our science question. We need to run this application. We just created an application to solve a real interesting science problem. The problem is we're going to experience a storm, and the question is are our pipes going to freeze? So I'm going to give you some additional information here. Outside temperature has been for a long time in the past 70 degrees. So that's a hint about something. It's a hint about what the initial conditions should be. The storm is going to last 15 and a half hours, and let's just say for laughs, when it starts, it immediately drops to 40 degrees below zero and stays that way for 15 and a half hours. That's, of course, not the way real storms work, but let's just assume that. The walls are 1/4 meter thick, and the pipe is 0.1 meters in diameter. And here are some material, we're using wood in this case, so you've got some material diffusivity. So I'm going to give you, we have a little bit of time, I'm going to give you about 2 or 3 minutes to come up with the right command line to run this problem. And by the way, when you do it, give it a different run name. Give it something like, for our uname, call it wall, so you do like this when you do. And then for other parameters, you can say like dx 0.5 or, sorry, whatever you need to set, dt. But you need to come up with a command line that basically sets boundary condition 0, 1, the initial condition, max time, delta time. You can leave dx at 1.0, the length, and the alpha. Yeah, I guess you need that information, don't you? Can't do science without the parameters there. Later on in the evening, we'll deal with some other materials. Or if you want to, if you're like really fast, because I know there's probably some people in here that's just like, this is easy. I could do this in an Excel spreadsheet, and as a matter of fact, you can. But try some other materials then, and some additional questions. Now, by the way, as you go through the lessons are asking you the questions I'm asking you. So make sure you fill in the forms what your answers are if you want to get points for prizes this evening. If you walk through that lesson, the lesson page, then all this information is in the lesson page. You get to some points where it asks questions here. Make sure you go to the Google Answers form and enter your answers. I'm going to basically enter the command line to run this now. All right, so I'll walk through this real quick. Basically, the material diffusivity is 8.28 to the minus 10. The wall is 1/4 meter thick. We'll leave dx at 0.1. You got to choose dt to maintain stability conditions. Remember that equation is only stable for combinations of these parameters that are appropriate. 100 is fine. Anything below 500 is fine. The remaining terms, we got to use temperatures in Kelvin. So those are basically the boundary conditions in Kelvin. That's minus 40 degrees Fahrenheit, 70 degrees Fahrenheit, and an initial condition of 70 degrees. So we'll let that run. It doesn't take very long to run at all. Runs very quickly. That's a plot that you should get. You should be able to get this plot. If you're not, I can help you get it later. But from this example, can you tell me whether or not the water pipes froze? Who here thinks the water pipes froze? So everybody thinks that they did not freeze. And okay, so what we have here is distance from 0 to 1/4 meters. This is temperature. This is the water freeze point, 273 degrees Kelvin. And this is representing the spatial position of the pipe in the wall. All right? And if you go to the center of the pipe, is the temperature above freezing? It is. So the pipes don't freeze. All right? Okay, so there are a number of other questions and stuff that you can follow on in this lesson later. I see I'm down to a minute, so I think I will stop there. And ask if there are, were you running into technical difficulties or just questions about this problem, either way.